Okay, so we just looked at the demonstration with the tuning forks, a demonstration of beats, and a demonstration of resonance. And we listened to the Doppler effect for a railroad train on YouTube. And I invite you to go and fool around and find some. There's probably way better examples in YouTube of Doppler effect than that one. That's just like the first one I found. Okay, I want to reinforce number 8 from the homework with you, in which you have two liquids at different temperatures, and you mix them together, different mass, different specific heat, and try to figure out the equilibrium temperature. And I saw a lot of people trying to sort it out. There was a nice YouTube video that somebody posted, but in office hours yesterday we worked it out, an example of it. Here's liquid R, 0.56 for the specific heat, 0.56 calories per gram Kelvin. We worked out this kind of a problem yesterday in office hours, and I want to show you the kind of the thought process that we did. I had to shut down homework number 17 for about an hour and a half yesterday because there were some problems with this calculation. I got it sorted out. It's working good now, but I gave everybody an extra 2 attempts. So everybody, hopefully you haven't burned all 6 of your attempts, but you have until tomorrow night if you haven't. If you still got attempts to burn, you can try them out anytime between now, Omari, and midnight Friday night. Okay. Now the objective is to figure the equilibrium temperature. Here are the two variables. Every time you take the quiz, the homework quiz object, it gives you 2 different temperatures. Now, when I did it this morning, it came up with 340 and 279. Yesterday, we had 276 and 337. And we worked it out. And so we'll work out this one. Temperature of the hot liquid N, 340 K, and temperature of the cooler one, 279. Now the hot one loses heat, so item 1D says this stuff loses heat. All right. And by the conservation of energy, we're assuming it's in kind of like a thermos, an insulated container, so no heat is going in. After we inject that drop, no heat is going in or leaving. All right, so the heat you have is the heat that you start with, but it redistributes itself so that the average kinetic energies and the temperature stabilize at equilibrium. So you've got this equilibrium. Supposedly, it better be between 279 and 340 Kelvin. And if it's not, you got trouble. It means you have miscalculated something. You've misunderestimated the temperature. Okay? And now, the thing that, we were working on in office hours, another student and I were working on this, the gap. We were focusing on the gap between those two temperatures. The hot temperature and the cooler temperature, the gap in this example is 61. Now, when you were doing it, you might have had 72 Kelvin. But the strategy you use for 61 will work for any gap that you've got, 72 or 102. All right? And the strategy is this. Try some token value of heat exchanged, lost by liquid N, gained calorie for calorie by liquid R, and figure out how that changes the temperature for liquid R, for liquid N. And then see how that closes the gap. All right, so in office hours, let's do something easy, 10. So we chose lose 10 from the hot liquid N, and we'll do gain 10 calories for liquid R in just a second. Here's the calculation. Minus 10 calories is the heat lost by liquid N. And Dante, it's M times C times delta T as always. But now we know what the Q is. We're trying to figure out what delta T is. And this is going to work out, the M times C, the mass of liquid N, times the specific heat of liquid N, is always equal to 168 calories per Kelvin. And if you were doing the homework, you might remember, I was working with 168 a lot on that problem. So you divide both sides by 168 and you get delta T subscript N. And remember, this here is your decision. And it can be a good decision or a bad decision or a medium decision, depending on the size of your gap. Right? Now, here's the similar decision for liquid R. Okay? Liquid R gains 10, so it's a plus 10 calories. M subscript R, C subscript R, delta T subscript R. So this is the mass of R, which in the way the problem is set up, it's always 120 grams. The specific heat is always 0.56 calories per gram Kelvin. And so those two numbers multiply to 67.2. So you may remember this number from working on your homework. 168, 67.2. So you divide 10 calories by 67.2 calories per Kelvin, and that gets you delta T for liquid R. Now that's under this proviso that you're looking 10 calories at a time. What's my delta T if I just let them exchange 10 calories? All right, here it is. Here's how you calculate it. All right, and it works out to this. Here's your results. You may recognize this from your homework. Liquid N drops 0.0595 Kelvin. Liquid R rises in temperature 0.1488 Kelvin. And that's all right. It's kind of small though. I mean, my gap is 61. So this is it's good, it's accurate, but it's kind of pokey. All right? Because it only squeezes down my gap by 0.2 Kelvin. And I got to do 61 Kelvins worth of squeeze down, so we're going to be at it till the cows come home at this rate. So then in office hours we're thinking, well, let's try a bigger number. Let's try something 100 times bigger, and that'll give me a bigger delta T. All right? So we said, all right, for my second attempt at delta T's, let's use a Q plus or minus 1,000. And here it is. And it's basically your delta T from the first one, but multiplied by 100. Because you're using 100 times more calories. Okay, so you're saying to yourself, all right, let me calculate the rise in temperature of liquid R if I have it absorb 1,000 calories from the hot droplet. And when you do, it comes out to 14.88. Same thing for liquid N. When you do your accounting and say, all right, how much does the temperature drop for liquid N if I drop 1,000 cals into the other substance? All right, it goes down by 5.95 Kelvin. Now that's not too bad. That's a little nicer because now I've got a squeeze down of about 20 Kelvin. Now let me ask you a question, and I invite you to venture a bold guess. How many calories should I try for my plus or minus to close the gap in one shot? 10 was too small. 1,000 is too small. How many should I use? 3,050. Let's round it off to 3,000. 3,000. That ought to get me down to, it's basically 3 times this. My squeeze down here is 20. So 3 times that, 3,000, ought to get me squeezed down about 60. Now, that'll get me pretty close. All right? Now, here's a table of my experiments, my Q experiments. Okay, first one, 10. We've already got the specs for that. Second one, plus or minus 1,000. We've already got the specs for that. Delta T subscript N, delta T subscript R. And do they add up to 61? No, but they squeeze down about 20K. All right. So my fourth column here is my squeeze down check. When that gets me 61, ding, I'm good. All right, next one, 3,000. Uh-oh, we got problems. Squeeze down factor, 62.5, a little bit too much. So go ahead and jot down this 3,000 row with negative 17.9 for delta T subscript N and 44.6 delta T subscript R. So nature would never do this. Nature wouldn't do this. Nature will not overshoot. It'll not overshoot equilibrium. It'll slowly dip and converge to equilibrium. This is too big of a close down. This overshoots. All right? So we were in office hours, and we tried 3,000, and we figured out, whoa, that's overshooting. That's too much. So we said, all right, let's back it up to 2,900. Okay, 2,900, too big. 30. And so, what's your first name again? George. George suggested 3,050, and had you done that, you would have had an even bigger overshoot. Okay, so you just back down. So we tried 2,900. We tried a bunch of numbers. So put ... for the fourth row of data, fifth row overall, to indicate, trying so 2,900 was not enough, and we tried 2,950. That was too much, and then finally, all right, let's go between. So 2,900 is not enough. 2,950 is too much. Let's go halfway between it, and we tried it. 2925, and ding, 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 pretty close to 61. We got 60.9 for my squeeze down, okay, which is good. And then my delta T for liquid N, I can't really see the screen here, so I don't know, my cursor's not on there. At the bottom of the second column, delta T for substance N is negative 17.4. You're dipping down. So in the cool down process, if you trade 2925 calories, liquid N is going to cool off by 17.4. And liquid R is going to warm up by 43.5 Kelvin. All right? So and those two add up to 60.9. Now let's check the equilibrium temperature. If you start liquid N at 340 K and then subtract 17.4 cool down, that gets you to 322.6. Okay, so if you go to the bottom, you get the 61 in the far right side, and your table's done, and then you say, all right, let me subtract 17.4 from 340, and I get 322.6. That's my equilibrium temperature. And if I do the same thing for my third column for liquid R, Sarah, I better get something close to that, if not right on top of it. So take 279 and add 43.5, and you get 322.5. And my wonderful students, That is within the plus or minus of 0.2 Kelvin that I built into the problem. Ding! You are done. Equilibrium temperature, 322.5, within the plus or minus that I set. All right? Now, as I mentioned, you can work. You don't have to use a table. You can just do a series of calculations in your notebook and whatnot. And then try to find 61 and get your equilibrium temperature. There's another way that a student. Are you here? The student that posted that, the video, the YouTube. It must have been the first hour class, the morning class. She posted a tip, and it's in discussions under video for homework 8 or something. It's one of the discussions. It has the word video in the title, and it's a nice little YouTube. The problem with the YouTube is it's a lot of algebra, okay? And this table pretty much bypasses a lot of algebra. Also, the YouTube doesn't really explain why she's doing a lot of the algebra, where she got it. Some of it she explains, but some of it not. But it definitely works, and you can look at that. And so between this explanation here in lecture today and that YouTube, see what you can do. And go try it out on your last 2 attempts if you still have them to burn. All right? See if you can do. And as always with all homework, I always select your highest score out of your 4 attempts, or in this case, 6 attempts. Question?
So there's no formula to find Q, you have to always guess.
To find Q, you make a guess, and then you decide if it overshoots or undershoots. If it undershoots, it's good. But even if you overshoot, it tells you to back up a little bit. So you just got to adjust your Q's, and that'll help you figure out your equilibrium. There is a formula for the equilibrium temperature, but it's a lot of algebra. And if we were in an engineering class, we would go through the formula, because that's what they. Well, we don't need formulas. We got a table here. We got brains. We could think. Colin. Repeat. Fundamental frequency. Fundamental frequency. Fundamental frequency is the frequency when Darian and I were up here demonstrating on Tuesday, and matter of fact, we're going to talk about it here in about 2 seconds. The fundamental frequency was when we had a bump alternating with a dip, oscillating dip up to bump, and that's the fundamental mode. The wavelength of it is double that. The frequency is, V divided by that lambda, and that's the fundamental frequency. And it was, I don't know, like 1 or 2 times per second. So 1 or 2 hertz. It's a few hertz. And you can figure it out. I mean, Colin, if we had decided to time it, count 10, time 10 full oscillations, and then divide by 10, and that would be your period. We could have done that, but all right. Let's talk about that beat frequency. And we started talking about this last time, and we set up this lovely, accurate set of diagrams. I said to myself, Dr. B, I want an accurate diagram with an easy-to-manage wave system. So I set the velocity of propagation at 80 meters per second. That's in the upper right of the screen. And then I chose a couple frequencies, 106.7 hertz and 119.5 hertz. And I chose those to be my frequencies, and then I mapped them out. The wavelength, and Colin here, as soon as I choose the frequency, I know the wavelength. You know, the lambda is equal to V divided by F. And so I have perfect graphs. The black one and the red one. The first one on top is black. The middle one is red. And if you mix those two sounds together, if they're coming through the same earpiece, or if they're both from the same location in the room, you're going to hear this down here. Make a note. This blue curve at the bottom, Jessica, is the sum of the first two. It is called the superposition of wave 1 and wave 2. Let me repeat that. The blue curve is the superposition of wave 1 in black and wave 2 in red. It's basically just adding them up and looking at the waveform. So this blue waveform demonstrates beats, and that is what you were listening to, although the speed of sound is 343 meters per second approximately, not 80. But this is what you were listening to. You heard loud, faint, loud. All right? And where the blue waveform at the bottom has a big amplitude, that's where it's really loud. And where it has a lower amplitude in the middle, that's where it's really faint. And these are waves, and they're moving past you 80 meters per second. So you hear loud, faint, loud, faint, loud, faint. That is what you hear as beats. You know, when we did these two tuning forks with this little clip, modifying the frequency and the wavelength just a little bit, we produced beats. Now, the frequency of beats, the beat frequency is just the difference of the two. So big minus little, in this case F2 minus F1. And that works out to 12.8 hertz. Pretty nice. The wavelength of the beats phenomenon is 6.25 meters. All right? And so at 12.8 hertz, and what you can do to double check me is multiply F times lambda for wave 1, F times lambda for wave 2 in red, F times lambda in blue for the superposition, and you'll come up with 80 all three times, because V is equal to lambda F. Okay, so these are sound. This diagram here is kind of a hypothetical sound wave system. Sound actually moves a little bit faster than 80. But you can also get beats with electromagnetic phenomena, and this is what I began telling you about last time. And a policeman uses radar gun technology to pick up differences in frequency between what he beams out at your car and what is bounced back from your car. He compares those two waves, and he'll actually find beats. And when he figures out the beats, he can figure out your speed. Now let's take a look at how that all works. It uses something called the Doppler effect. And the Doppler effect is that change in pitch. So a Doppler effect always happens when you have motion between the observer and the source. So if your source is stationary in the freight yard and you're moving, you're going to experience a Doppler effect in what you hear. If you're standing by the side of the road at the corner of 5th and Main and you listen to the train as it goes past, and that is what we saw on YouTube, you'll hear the Doppler effect as well. So relative motion between observer and source is what you need. So if everybody's stationary, you might have a train horn that blares out at 113.2 hertz. All right? But if the train is moving toward you, the frequency that you hear is going to be a little bit bigger. It's going to be a higher pitch. All right? So here's what you got to remember. In that YouTube video, what we didn't hear was the sound of the train horn when the train was stopped. We only heard it when it was coming toward us and then when it was moving away from us. So we didn't hear the stationary sound. But whatever that stationary sound, it was something less than the sound when it was approaching. And then as it moves away, it passes by that cameraman, the guy that's out there videoing it up, and using a little video camera, just like the one that we use today. And as it moves away, it is at a lower pitch. The sound comes to him at a lower pitch. And the same kind of thing is used with a radar gun. So if the police officer is parked on the corner of Alafaya and University, and he beams out a certain frequency, the store-bought frequency or the factory setting frequency, he knows what that is. The factory designs his radar gun with a certain frequency. Now, if you're moving toward him, it's going to come back at slightly higher frequency, depending on how fast you're going. If you're moving away from him, it's going to come back to you, but at a slightly lower frequency. All right? And I'm going to show you how that works. This is how they nab you. Now, this fancy relativity formula, F return divided by F send, is equal to the big square root. Now, for radar, the quotient V over C. V is the speed that you are moving. C is the speed of light. So V over C is a fraction of the speed of light that you're actually moving. Now, I'm not going to show you how this comes out of the theory of relativity, because this guy has got it programmed into his radar gun. But what he does is he measures the return frequency from the car. He's got a radar emitter and a radar antenna, and he listens. He sends out a pulse, and it comes back at a slightly different frequency. Okay. He knows the frequency that he sent it out. That's the factory setting. And he also knows the speed of light. So he can figure out everything in here and solve for V. And it's a lot of algebra and stuff. We're not going to work through the algebra on this. You could mess around with it if you want. But if the return frequency is higher than the factory send frequency, that means this quotient is going to be greater than 1. If the return frequency is slower than the send frequency, the factory setting, then this fraction is going to be less than 1. All right, but you'll still be able to figure out the speed at which the car is going. So, for instance, the computer solves for V, and here's an example. If the factory setting is 100 gigahertz, right, for radar, right, that's up in the radar region. Wavelength 3 millimeters. Then he might get a return signal just a little bit above that. Go ahead and write down all the digits. Let's see if I can count it. 1, 0, 0, 0, 0, 0, 0, 2, 6, 6, 8, 5.132 hertz. All right. So that means it's higher than 100 gigs. Okay, it's a little bit higher. And here's the beat frequency, 26,685.132 hertz. And he'll be able to measure that much precision. And then he plugs it into his radar gun automatically puts it into the computer, and the computer lights up his display, and it says 89.5 miles an hour, and he knows that it's coming toward him because this frequency is higher than the factory. So his fraction, F return over F send, is a little bit bigger than 1, and his computer solves the square root, solves for V, and gets everything squared away, and then gives a ticket to whoever this is because they're going at 89.5 miles per hour. And that is how they nab you for speeding. And it drives me insane because I got nabbed for going. He told me I wasn't going 35, I wasn't going 36, I wasn't going 38, I wasn't going 40, I was going 37. He knew to the nearest mile an hour. And probably could have put it to the nearest hundredth of a mile an hour if he wanted to, because the precision on these devices is in the parts per billion, a few hundred parts per billion. That is really, really good. Okay, so it's kind of hard to beat these guys, unless you can prove that he dropped it in his soup, or he accidentally ran it over, or put it in his microwave and nuked it with his breakfast or whatever. These guys, you can't beat it. Unless you know the frequency, the send frequency, and you send back, that might work. If he's sending and you send back something at, lower than that, you can maybe spoof his system, but I better not tell you how to do that because I might get in trouble with the cops for telling you how to beat the radar gun. Now, Colin. Harmonics, fundamentals. Do you guys want to dismiss early today? I think we'll be able to dismiss early today. A few minutes anyways. Now, last time, this is our last set of notes here, but let's go through it. Oh, we have some clicker questions. So have your clicker out, because I have a clicker question about this set of notes here. What does it mean to have a harmonic? You hear musicians, oh man, I'm getting a harmonic. I'm getting an overtone. All right, harmonics and overtones. Let's talk about what that means. And we'll go back to the coil spring that we looked at in class on Tuesday. When Darian and I were up here in the front, we were maybe about 3 meters apart. So the distance between us was 3, and so that was half of a wavelength. That's a bump oscillating with a dip. Right, so the full wavelength, lambda, and Lindsay, I'm going to give this lambda 0 as a subscript to denote the fundamental. The fundamental wavelength is 6. Now, if I knew what the wave speed, or if I measured, I could tell you what the fundamental frequency was. It's not hard to do. We should have done that, Darian. I'll have to try that another time. But you can figure out the fundamental frequency, whatever it is. I'd estimate it's going to be 1 or 2 hertz, somewhere in there. Like 1.35 hertz or something. Okay? So we had that thing, and I had to oscillate my end of the spring at that rate, and if I did that carefully, I got a standing wave. The first excited state. Now, Caitlin, that was a full wiggle. We got a bump and a dip. And they oscillated with a dip and a bump. All right, that's one full wave. So that means that lambda 1, the wavelength of the first excited state, is 3 meters. All right, so the fundamental has the longest wavelength, and the first excited state has half that for this system. And now carefully look at this set of equations here. Frequency 1, the frequency of the first excited state is equal to V, whatever that happens to be, divided by 3 meters, lambda 1. Right? So F1 equals V over lambda 1. Lambda 1 is the same as lambda 0 divided by 2, half of lambda 0. So over here, I'm going to push this forward so I can see what I'm... So right over here, in the third stage of this set of equals signs, it's V over lambda 0 divided by 2. All right, divide by 2, and the denominator of refraction is the same as multiply by 2 in the numerator. So the fourth stage right here, 2V divided by lambda 0. But V divided by lambda 0, Colin, is fundamental frequency. That's from 1D. F0 is V divided by lambda 0. So F1 is 2 times the fundamental. And that is why it is called the second harmonic. All right? The second excited state would be the third harmonic. Etc., etc. And in general, if F0 is the symbol for the fundamental, so like C sharp, whatever that is, and then its second harmonic is, or its nth harmonic is going to be n times whatever the frequency of C sharp is. All right? So the nth harmonic is n times the fundamental frequency. And that's how it goes. So let me check your brains with a clicker question here. All right? And my clicker question for you is, if you're ready, get your clickers open. C sharp. C sharp number 4 is 278 hertz. Its second harmonic is which one of those 4 frequencies? $278 is what? What is the frequency of the second harmonic of this C sharp? Okay. So the frequency, so this is F0, 278. What's the frequency of its second harmonic? Leah, did you click in an answer? Good. $30 seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Very good. Uh-oh. Some of you chose 139. No. That's half of what it of the 278. You want to go double the 278. All right, next topic, the Van de Graaff generator. Have you ever seen this like on PBS or Discovery Channel or something? This device where they rev it up and the electricity, it makes your hair fluff out. Now we're going to do this on Tuesday in lecture. And so if you want to try it, you're not dismissed. Not yet. In a minute. So if you want to try this in lecture, before you sneak out, wash your hair on Monday night and don't put any conditioner in it. And we'll ask for volunteers. And if the weather's still really dry, it might work. I am going, last announcement, it's pretty important. I am going on a camp out this weekend. So I'm not going to be going on web courses, and for that reason, you don't have any regular homework. Just read the electricity chapter. And we'll see you on Tuesday. Now you can go.